Alright, Dr. Calkins here with week 5, chapter 5, and this is the end of this chapter when it gets into naming. So we're going to break this up into 2 smaller videos because it's a lot of information. This video is going to be based on binary things. Just remember that binary, like a bicycle, is 2. Ionic would be, in this case, a metal positive and a non-metal negative. So when we think about these, what we have to mostly think about is what we've seen in exam 1, and that's charges. Charges are predictable by family. So remember, as we look at charges, group 1 is going to be a +1. Group 2 is a +2. These were a mess, but now we have to deal with them. We'll get back to that. When things are predictable, remember they change based on this dark line. That's the metalloid line. That's when they change from being positive to negative. And we did this together in Supplemental 5. I just stole one of the empty ones from one of my blank copies. So here's going to be a +3 for that aluminum family. This is a +4 for the tin and lead family. We're not really going to deal with any of those, so don't worry about them too much. As we go to the other side, this is the noble gases, they're neutral. These guys, again, -1, -2, -3, -4, so I'm going to stay sideways to make it look prettier. Again, we're going to deal with those, and you should have this in your lab book already. We're just reminding you of where to find these answers, and we're probably not going to deal with boron at all. So that's what we've seen so far in exam 1. We just haven't named them. What's important about this one is now we deal with transition metals too. Transition metals usually are going to have a +3 and a +2 in this little region. The ones that we typically deal with here is probably iron, right, kind of in the middle. And as we go to this lower edge, we're going to be a +2 and a +1 for copper. Zinc's a +2, cadmium's a +2, silver's a +1, notice, just like copper, but it's only a +1. And then you might see the mercuries, which are +2s and +2s. This is just a +2/2, so it's really a 1, and that's even weirder yet. So notice it is kind of in sequence, +3s, +1s, and then these 2s. The reason these are all 2s is because they have 2 electrons over here to lose. Given their family, they're either going to lose a 4s2, a 5s2, or a 6s2, and that's the case. And it's also true that these over here that are not metals of the transition type can move charges, and these are main group metals that also like +2s. So the tins and the leads, they like 4s and 2s. So, given that in mind, we have a predictable chart. After you take the dizziness away of flipping the table around over and over again, this is what we're looking at for the early part of this chapter. Predictable charges, and then now this new set of charges along with tin and lead to deal with. But what's nice about binary ionic is they end in IDE. So if they end in IDE, they're very easy to recognize. There's very few exceptions that aren't binary that end in IDE. The metal itself, so it's the non-metal that ends in IDE, so that's these guys over here that end in IDE. The metal is just the name off the periodic table. So this is where we would use something like Na and Cl. Na is a +1, so it's going to be sitting over here. Chloride, 2 halogens down, sits over here, so it's a perfect match, +1, -1, they cancel. And that's what we would have done on exam 1. But now instead we're saying sodium chloride instead of sodium chlorine. So that sodium chloride idea, important for this chapter because binary ends in IDE. What we have to watch out for though is what if we had iron with chlorine? Well, there's 2 ways to name it. And if this were the case, you either have a 2 here or a 3 here. Let's say this is a 3. If this is a 3, that means that it came from iron's charge of a +3. This was a -1, so this was an imaginary 1. So there's 2 ways of naming this. There's the stock system, which is the new system, but it's also the system that is not used very often by companies. We would call this iron 3, its charge of 3 in parentheses, and then chloride. So notice still ends in IDE. But we can also name it based on its traditional name, its very fundamental Latin name, which is ferrum. We can use ic versus os. Ic versus os is a Latin system, and what's important about it is the ic is always the higher charge, os is always the lower charge. So if iron has a 3 and a 2, because of its location in the periodic table, this is a 3, it's a higher charge, we would call this ferric chloride. So you're likely to see some of those along the way as well. Sometimes you have to cross charges when there's things that are different, so let's think of something like Cu3 and 2. So remember, these charges would be reversed, just like they would have been crossed in a previous chapter. So this tells us the two names. It tells us the copper was a 2, because that was the 2 that crossed over to nitrogen. Nitrogen would not be nitrogen anymore, it would be nitride, so IDE ending. And then this 3 is back for nitrogen, that's what we'd expect given its family location of a -3. But copper has a 2 and a 1. So unfortunately in this case, the 2, unlike for iron, that would have been ferrous for iron, it's actually cupric for copper because its lower charge is a 1. So you have to pay attention on who's got who as far as charge, especially for transition metals, still ends in IDE. So that is binary compounds in essence. If you're a binary compound like these though, you can also have a binary acid. So if you're a binary acid, expect your IDE ending to go to a hydroic acid. So a hydroic acid is what we'd expect for any kind of binary acid. So if we were to put, say, a hydrogen and a chlorine together, we would say hydrogen chloride, but it would make hydrochloric acid. So a fun way to remember that, and this is where we'll end this lecture, because you won't see too many of these, but just remember IDE will make a hydroic acid. You can remember something like myride as hydraulics. Spelling hydraulics incorrectly on purpose. Myride, IDE, gives you a hydroic acid. So that's an easy way to remember those. Just remember that if you have acid, you're going to have H+, and then some other partner. So binary acids definitely have to have H+. The example we gave was H+ and Cl negative. That makes HCl. HCl would be called hydrogen chloride, but also hydrochloric acid. So the ide of chloride became a hydroic acid. And that's binary in a nutshell. We'll come back with another video for ternary. Alright, so Dr. Calkins again, we're going to add a little portion to the previous video. This is over binary covalent. So it's very similar. Binary still means 2, but covalent now means both are nonmetals. So if a nonmetal and a nonmetal get together, that's usually through dot connections, Lewis dot structures, which was the early part of this chapter. So we made a joke about one of these earlier, and that was water. In order to deal with these, we use prefixes, because there's no way to know how these connect the dots. They can connect in lots of different ways, single doubles, triples, multiple doubles, and so forth. But the prefixes we're going to deal with are mono, di, tri, and tetra. These are only used in inorganic chemistry. As you get to organic chemistry, these will change to meth, eth, propane, butane. So we'll see that later in a different chapter. But these are the 4 we need to worry about first, and then after that, the ones that stay the same for both chapters, we have penta, hexa, hepta, octa, nona, and deca. So there's our top 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So a couple of these are going to be relatively easy to recognize based on your experience with driving cars and so forth. But as we name things like water, H2O, we can use the numbers to tell us how to name it. So here we would say dihydrogen. So notice binary still has the first element, the one that's least electronegative, to be just like it is on the periodic table. But then the second one, instead of saying oxygen, we would say oxide. We could say monoxide to make it even more intimidating, but oxide is fine. It's kind of redundant to say mono in a lot of cases. One where it is kind of common though is here, CO. There's only one of each, so we do say carbon but because there's only one oxygen, we say monoxide. So notice we're using that mon for that one in its name, just like we use di for two in its name. So the prefixes always precede the element, although in the formula itself it actually comes after. So be careful of that. If we had CO2, notice it would change to carbon still, but now dioxide. So 2 for the 2. So any kind of combination would work. If we have a N2O4, we could now say di-nitrogen, and then now we could say tetroxide. Sometimes you could put tetraoxide with those two vowels together. It seems kind of weird. Most everything you're dealing with is just dealing with those prefixes and multiple choice kinds of formats in the homework and the tests. So as you look at any of those, just be aware that they can change. Even if we have a P4, let's say S10, we have 4 here, so that would be tetra. That's phosphorus. And then S10 would be deca, sulfide. What's most important about any of these, the prefixes are used because we're not crossing charges, and more importantly, they all end in IDE, and that's the case for all things binary. And this should finish binary compounds altogether.